Okay, good morning, brothers and sisters in science. If I can bring you all to order, we're going to have the first of our science novelty items. I'm Professor Hal from the University of Brighton. I'm Professor of Public Understanding of Science there. And this over here is my science homie, Kofi and Profi. Give it a butt for Kofi, please. Right, so it's my absolute pleasure to be here, I think, for the 10th year at Fisher Science World. And before we start, I need to get the health and safety sorted out. Fisher, they're so picky about life-changing injuries. No, seriously, you know, the odd death here and there, the odd life. But anyway, so we're doing live science. It's going to look chaotic and unrehearsed, but actually it should be. And we have to do these things called risk assessments, something like that. Anyway, so you'll probably be all right. Okay, so we're doing items involving fire. So in the unlikely event of a reaction getting out of control, I will let you know, and you will leave via the fire exits, which are signposted there, right after me and Kofi, of course, because it's scientists and strapping young assistants first. And the thing is, I got a really unusual chair. I got a chair in Public Understanding of Science, which means literally evangelising the science. And I get to travel the world doing these science shows and so forth. And I really love it. And the thing about it is, if you love your job, you never do a day's work in your life. You get paid to do your hobby. And so I really want to get that infectious enthusiasm to my students and school children, but also science is for everyone. And the mere fact that we're here talking to each other means it's for us too. So, I want to talk about some GCSE science first and remind ourselves where we are, and then we can get into some demonstrations. And in particular, I want to talk about the states of matter. I know it's like GCSE stuff, so there's 3 states of matter: solids, liquids and gases. And because they all hide in plain sight, we don't really think about it. So solids melt into liquids, liquids boil into gases, gases condense into liquids, and liquids freeze into solids. And our frame of reference is water. The centigrade scale is based on the properties of water. 0 and 100 are 2-phase changes of water. And I've got a little girl, and when I put her in the bath from time to time, she says, "Daddy, Daddy, it's freezing." And I say, "Are you really changing from the liquid phase to the solid phase?" And she says, "I want my mummy." And then alternatively, I'll put her in the bath, she'll say, "Daddy, Daddy, I'm boiling." And I say, "Really? Are you turning from the liquid phase to the gas phase?" And she says, "I wish mummy married an economist, not a chemist." Anyway, the point is, we associate boiling with being hot because water boils at 100. We associate freezing with being cold because water freezes at 0, and yet lots of things boil when they're cold, lots of things freeze when they're hot. For example, we're surrounded by boiling nitrogen, and yet I don't see any of you writhing in agony because of the temperature, because nitrogen boils at a very low temperature. And this watch band of this watch is made of frozen steel, and yet it's quite comfortable for me. So one of the things, I'm all into learning outcomes. One of the things when you walk away, apart from the witty dialogue and the handsome presenters, that you remember is a couple of things about rejigging what boiling and freezing mean to you, because they mean different things to different people. Anyway, so we're going to sort of talk about this a little while, and solids, liquids and gases, ice, water, steam. Have you got kettles, buddy? Thank you. All right, so in order to introduce that, we're going to sort of talk about gases in general, and then we're going to come in and talk about some particular gases. And the theme of this particular bit of the show is about gases that are denser or less dense than air. And the first one of those is helium. Now, helium is named after Helios, the god of the sun, because the sun is a huge fusion reactor squashing together hydrogen atoms to make helium. And when it runs out of hydrogen, it'll start squashing helium to make lithium and so on and so forth, and become a red giant. And then we are going to have some global warming because we're going to get swallowed up by it. But anyway, I know that you know that helium makes your voice go up in pitch, and I've got a real problem with that. There's this misuse of helium. Helium is a non-sustainable resource. It's produced It's produced in the earth. And the fact of the matter is, unlike many gases that you get by the fractional distillation of air, helium comes from helium mines. And when you get that balloon from McDonald's and breathe it in and make your voice go up, it radiates out into space because it reaches escape velocity. So it'd be really, really irresponsible of me to breathe in helium just to get a few cheap laughs, wouldn't it? And I mustn't do that, all right? But if I'm educating you, it does work, because we need to know, why does helium make your voice go up in pitch? The frequency of your voice is dictated by your larynx, and your larynx moves at a certain frequency in air. Helium is 6 times less dense than air, and so your larynx vibrates faster. So we're going to test it out. Now, I need my main man, Kofi, next to me, because the thing about this is you get hypoxic quite easily. So why don't you do it?
Remember the last time?
Yeah, you do it. So just introduce it. I am Kofi Amprofi.
I am Kofi Amprofi.
Right, okay, so Kofi's going to take 1 lungful of helium. Okay, do it.
Still Kofi Amprofi.
Ah.
Stop laughing at him. Respect his authority. Look, they're laughing at us. I'm a professor and they're just laughing at a serious scientific experiment.
Anyway, so that's helium for you. And I actually wondered, if we can all hold our breath for about 20, 30 seconds, why is it that helium can make you hypoxic? Because one of my kids did that once. They breathed it in a McDonald's and he fell over. And it's because if you're holding your breath and your lungs are full of air, you've still got a diffusion gradient. Oxygen's diffusing, albeit slowly. If it's full of helium, you've got nothing, which is why you can get hypoxic in a few seconds. But anyway, I know you didn't come up the way to Leicester to listen to me with a high-pitched voice, so I want to test my theory. We've got a gas that's 6 times more dense than air, called sulfur hexafluoride, and if my theory is correct, my voice should go down in pitch, all right? Now, take it seriously, all right?
Is it working yet? Oh, it is working. I like my voice like this. I sound like Barry White. So the sulfur hexafluoride gives me this manly voice because my larynx is vibrating slower. Isn't it great? It is amazing. Give it up for the sulfur hexafluoride. Right, so our big learning outcome, I'm sorry, the struggle I have with this is it's 6 times more dense than air, so I have to really push it out. Helium's 6 times lighter than air, but actually it's quite lipophilic, so you can get that kind of general anaesthetic type thing. You're right standing there, mate?
Yeah.
Excellent, right, okay. So we're going to move on a bit. So solid, liquid, gas, that is the rule, and we're going to now look at the exception to the rule, because some things don't quite do that. This is carbon dioxide. It's solid carbon dioxide. I love the smell of CO2 in the mornings. It's solid carbon dioxide. It does a very, very interesting thing. It sublimes, and that means it goes straight from a solid to a gas. And it does that at a temperature of, what's the sublimation point of carbon dioxide? Oh dear, we're at Fisher's. It's minus 78. So there's 2 questions I've got for you. If it's minus 78, which is colder than Kofi's living room in the middle of winter, if it's minus 78, how come I can hold it in my hands? Well, there's 2 reasons for that. The first reason is I'm a really brave trooper and I have no pain threshold. The second reason is the Leidenfrost effect, which means that the CO2's subliming on my hand and creating a warm amount of air which protects me. But I certainly shouldn't hold on to it for too long. And I certainly shouldn't put it in my mouth, because then I'll get all... Oh, that really hurt. Now look what you made me do. Anyway, it didn't hurt at all. That's CO2 for it. And of course what I should have said at the beginning of the show is don't do any of these at home, like you've got loads of liquid nitrogen or CO2 at home. Anyway, what we're going to do is I want to make an elegant demonstration with CO2 and some hot water. And to do that, I'm just going to pour it in here. And we're going to do 3 or 4 learning outcomes just with CO2 and hot water. So that's the hot water in it. CO2 is very, very unusual. There's very few things which sublime. Iodine sublimes, CO2 sublimes. And also, curiously, ice sublimes to a certain extent. You know when you get sort of, it's cold and it snows and the ice disappears anyway, it's because it's subliming. And freeze-drying coffee is the same principle. When you freeze-dry it, you let the water sublime off so you don't lose all the nice stuff, the nice flavours of the coffee. Anyway, have you got any, the chemistry balloons, where are they, buddy?
What's down here?
Why have you got a big box like that?
Need them.
Anyway, these are our chemistry balloons. We're not allowed to call them anything else. They're chemistry balloons. But what have you... Really? Busy last night. Busy night, was it? Do you know how to use one of... Do you know how to do it? Hang on. I've got 4 kids, if only. A lifetime of paying out versus 50p from Boots. Anyway, that'll learn me. Right, so this is a chemistry balloon. What we're going to demonstrate is that, well, 3 things. First of all, that solids occupy far less space than gases. And we're also going to demonstrate sublimation. And you'll be able to see the CO2 subliming. All right, so I'm going to take 1 handful of CO2. I'm going to dump it in here. And straight away, we see it's producing an awful lot of gas. And what we're going to do is, we're going to put our chemistry balloon up here and hopefully demonstrate that 1 handful of CO2, that is a... Well, yeah, give it up for the CO2 balloon. So, what you can see is, if you look, you can see the CO2 is going directly from a solid to a gas. Very, very unusual. So the solid CO2 is producing gas. And the white vapour isn't CO2, it's just this is so cold, it's causing air to condense. So it's a cloud factory, so it's air. Now, the other learning outcome is, where's the white water vapour going? Is it going up or down? It's going down. So we've proved CO2 is denser than air. So 2 or 3 really, really lovely learning outcomes. So that's CO2. Now that's at minus 78. So minus 78 is fairly cold, but we're going to go a little bit lower because if you take any gas and you cool it down enough, you get a liquid. And what we've done is we've got some effectively liquid air. And the first question that you might be thinking, if you're curious about it, is how do you get it? How do you cool something down to the temperature of liquid air, which is minus 196, which is liquid nitrogen? How on earth do you do it? Well, what they do is they use what's called Joule-Thomson cooling. They compress it, they let it expand, and it's like an aerosol. Do you know in the days when we had aerosol deodorants, it was always cold because it's an adiabatic expansion pushing the atmosphere back, which costs you energy. And if you do that a certain number of times, eventually you get a liquid. And we have some liquid nitrogen. It's right here. And I mean, it's really, really convenient way of getting low temperatures in the lab, and it's relatively inexpensive. It's about 5p a litre. And the thing about it is, you can see it's boiling, and this is what I was talking to you at the top of the show about, is redefining the definition of boiling. Boiling doesn't mean hot. Boiling means one thing and one thing only. Boiling means changing your phase from a liquid to a gas. Now, as soon as the liquid nitrogen touches that glass, the glass is at room temperature, so it's 200 degrees above the boiling point of the nitrogen. And so it starts boiling, and in a little while it's going to settle down and reach an equilibrium. And the interesting thing about that is the inside of the glass will be at minus 196, the outside will be at room temperature. So this is a Dewar flask. It's like the flask you put your coffee in, except it's much heavier duty because it has to withstand that terrible expansion and contraction. So we're going to do some nice demos with liquid nitrogen. So can I borrow you, please? Okay, some safety glasses, please. What's your name? Louise. Give it up for Louise, please, our science lab rat. Sorry, I shouldn't have called you a science lab rat. Right, okay, now, have you ever taken a shower with a professor before?
No.
Okay. Well, day's not over yet, is it, right? So this is copper tubing, and it's at room temperature. Room temperature is comfortable for us. As far as the nitrogen's concerned, it's 200 degrees above its boiling point. So it's like putting red-hot steel into water. That's a nice analogy. So what's going to happen is we're going to put the pipes into the nitrogen. The nitrogen's going to boil. It's going to turn into a gas. The gas is going to expand, and it's going to spray myself and Louise with liquid nitrogen. You might be all right, and the hair will grow back eventually, okay? So, stand next to me, closer. Thank you very much. All right, are you ready for this?
Not really.
All right, it might hurt a little bit. Well, a little bit's all relative. So 3, 2, 1. Okay, don't forget behind your ears, please. Isn't that refreshing?
Lovely.
So, give it up for Louise and her liquid nitrogen shower, please. Isn't that great?
Lovely.
Okay, yeah, well done. All right, so thank you very much. All right, so liquid nitrogen shower. I just want to sort of dwell on the nitrogen just a little bit because I think it can be quite fascinating once you're absolutely getting into it. And The thing about it is, the nitrogen's just sitting there quite peacefully, minding its own business. But there's lots of things we can do and look at the various properties of things. And one of the things...
Please, Jamie Gallagher will be giving his keynote speech in 15 minutes' time. Please make your way upstairs to the Premiership Suite before the doors close. Thank you.
It's the B team, all right? Because we is the A team. Right, okay. So, one of the lectures, the thing about being a lecturer is you can almost lecture on what you want. And one of the things I do lectures on is I'm very interested in disasters that didn't have to happen. So I do a nice lecture on Chernobyl. And I didn't like the Sky Chernobyl series. There was lots of inaccuracies. But it's one of those things about safety when folks they cut some corners and the levels of redundancy get reduced and suddenly we are where we don't want to be. The other thing is the Space Shuttle Challenger. And I like the stories, all right? So I tell lots of stories, and this is one of them. The Space Shuttle Challenger was a $10 billion aircraft which was destroyed for the want of a $20 piece of rubber. It's as simple as that. Piece of rubber and some corner cutting. Now, in the year that it happened, the public had got bored with the shuttle. It was routine. It was literally an expensive way of putting stuff into space, and all the cost savings that they'd imagined by using reusable rockets weren't materialising. It was actually very, very expensive to reuse them. Moreover, this was about politics as well as science, because the company that made the solid fuel boosters was called Morton Thiokol, and in order to share all the various work, they were chosen. They worked out of Idaho, which is landlocked. So the boosters had to be delivered by barge in sections, and that's the key thing. And if you know anything about engines, you know that if you've got a section under stress, you have to have a rubber grommet to keep it safe on a bigger scale. So an oil seal in a car, for example. Now, on that particular day, it was very, very cold. It was actually colder than the specified operating temperature for launch. And NASA put a lot of pressure on Morton Thiokol to authorise. And there was lots of toing and froing, and they cancelled the launch 7 times, and so there was a massive amount of pressure, and in the end they agreed. They relented, even though the temperature was well below the specified temperature. The space shuttle liquid fuel is liquid hydrogen and liquid oxygen, which you can imagine is explosive. The solid fuel is ammonium perchlorate and aluminium. And what happened was, when you see the film of the crash investigation, when it took off, as it started igniting, you see a big black puff of smoke coming out, and that was this rubber tube, not this one of course, but a rubber tube was too brittle and too cold to expand in time, so there was a hole in it, and it got stuck with powdered aluminium. And that kept it safe for about 73 seconds, but then the powdered aluminium blew out. A flame started coming out, and it burnt the strut holding the solid fuel to the liquid fuel, and as soon as it burnt it through, we all know what happened. Now we can demonstrate this property. This is a rubber tube. It's flexible and we can pull it apart. I'm going to put it into the liquid nitrogen, and I mean, rubber's an elastomer, isn't it? Isn't it? I taught you that in first year, buddy. So it's all basically like little springs, bouncy little springs, and as you cool it down, it gets more brittle. It's like if you go to buy some chewy sweets on a cold day, they're much more brittle than on a hot day, Starburst or something. So if we pull it out, now when this breaks, as it will, I'm going to do it behind a safety shield, but there might be a bit of rubber heading your way, so be aware of it, please. All right. So now I've told you, it's your fault if it goes wrong. Isn't it? Or it's Kofi's fault. Right, okay. So we're just going to let that cool down a little bit. Right, okay, so the same rubber tube, only ultra cold. And it breaks. It shatters like very strong glass. Okay, so the other thing I think we can illustrate quite cutely is this. This is ice, and ice is cold. So we all agree on that? Ice cubes are cold. So there's not much energy in an ice cube. But ice, if it's at -5, is still 191 degrees colder than the boiling point of nitrogen. So if I put ice into liquid nitrogen, as far as the nitrogen's concerned, this is like putting red hot steel into water. It's well above its boiling point. So I'm rather hoping the nitrogen's going to boil. 3, 2, 1. And there we go. So when you go away today, one of the sort of 3 learning out, there's always, everything happens in 3s. Try and remember 3 things. One of the things is we saw something boiling by the energy of an ice cube, which I think is relatively elegant. So give it up for liquid nitrogen, please. Right, okay, so we're coming to sort of the end of this little term. We've got a couple of more demos to do, and then we'll bid you farewell until the next show, which is in 1.5 hours. One of the things we can do is show you Charles's law. Do you remember Charles's law? What? You've been doing science with Charles? Hold that. Charles's law. Charles's law says that the volume and the temperature of a gas are proportional, i.e. the colder it gets, the smaller it gets. So what we're going to do is put some liquid nitrogen into here and put a balloon in it. Let's just borrow that, please. So if you heat a gas up, it expands. If you cool it down, it contracts. So if we just stick this balloon in here, we can see that it's withering like Kofi's hopes and dreams and becoming limp and flaccid. Who'd have thought I could get that word into a science show, mate? All right, so this is happening because the molecules are losing energy. They're moving closer together, and therefore the pressure's going down, all right? And I know it looks like the balloon's popped, but with a bit of luck, it hasn't. And I'm just going to try and not to super cool my my hands. Yeah, you'd like that, wouldn't you, mate? All right, so if we bring the balloon out, it looks pretty flat and useless, but as we let it re-equilibrate with ambient temperature, the gas starts re-expanding, and with a bit of luck, it'll all go back to the way it came from. There you go, buddy. Give it up for our amazing balloon. Right, so we're going to sort of finish off with a bang for no particular reason other than what? Not that. Oh, mate. Other than why wouldn't we? Now, normally this science show is peppered with explosions, but like I say, fish are really, really picky if we have life-changing injuries in a science show. And so we're going to do a sort of fairly non-hostile set of explosions. This is hydrogen. Hydrogen, the simplest of all elements, 80% of the universe, hydrogenesis, water creating. And that's because hydrogen, when it burns in air, produces water vapor. So normally I do 3 hydrogens and 3 hydrogen plus oxygen, but I understand that you all want to keep on hearing for the present time, so I'm not going to do that. I'm just going to do the first one, and then we're going to wish you a good day. So if you don't like bangs, this isn't the show for you. If, on the other hand, you do, you might want to put your fingers in your ears. You are not a chemist. You might want to put your fingers in your ears. You will feel the heat, but it's momentary, okay? So 3, 2, 1. That's 1. That's 2. That's 3. If you like the show, I'm Professor Hal. If you thought it was rubbish, his name's Kofi. Thank you very much. See you in an hour and a half.